S. Chan presents educational video lectures. Difficult concepts made easy. Study anywhere, anytime.
Adiabatic flame temperatures plays a major role in thermodynamic applications. Welcome to S. Chand Academy and I am Dr. Anmol Bhatia. We are learning the course Applied Thermodynamics, and in this we will be learning the concept of adiabatic flame temperatures.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box.
So the topic is adiabatic flame temperature, and first and foremost thing is we have to look at the definition part. So adiabatic flame temperature, in short, it is written as AFT, and it basically represents the maximum temperature achieved during a combustion process. And why it is called adiabatic? It involves no heat exchange. That means there is no heat exchange with the surroundings. So what we have to pursue in this adiabatic flame temperatures, it basically is a kind of the maximum temperature value which is achieved in the combustion process, provided that there is no heat exchange to the surroundings. So what does it basically serve? So it basically act as a very critical parameter in engineering applications, particularly in terms of combustion systems, chemical reactors, or you can say the propulsion systems. So we'll look more into the details. As far as the definition or the bookish definition is concerned, so adiabatic flame temperature is basically that temperature or that process. Adiabatic process is that process without any heat transfer which is there to and fro from the surroundings. So we cannot send the heat to the surroundings, and the surroundings from the surroundings the heat cannot flow inside the particular system. So AFT, which is adiabatic flame temperature, it is basically determined by the balance between the heat released during combustion and enthalpy change of the reacting mixture. So this concept is basically critical in calculation of the heat balance. So this calculation basically considers the energy released from the combustion reaction and then the sensible heat of the products. So there are things involved in calculation of this, which is basically the energy released and the sensible enthalpy of the products. We'll look at the formula of calculating this term, which is adiabatic flame temperatures, in the later part. But before coming to the the formula aspect of this particular property, we have to look at the application areas in which this is concerned. So first and foremost is the area of combustion system, then you have this chemical reactors, and later you have this propulsion systems. So what is the application area of this adiabatic flame temperature in combustion systems? Basically, when we want to design a particular combustion system, be it the calculation of energy efficiency or any other significant term, this adiabatic flame temperatures plays a major role in design of that particular systems. It is basically a significant term that plays a major role in designing that combustion system for efficient energy production and pollution control as well. So what we can achieve, we can basically optimize these combustible or combustion conditions based on this adiabatic flame temperatures. So industries basically can achieve this higher efficiency value, and then those emissions can no doubt reduce. There are application areas such as you can say the power generation area as connected to the combustion systems, the automotive engines and the heating systems, which are basically correlated with the combustion processes. Now, the second aspect is the chemical reactor, which is particularly the case of conducting a process which is a chemical reaction. So, this this adiabatic flame temperature is basically used to optimize that reaction conditions. So, there are particular conditions with which those reactions takes place inside the reactor, and this optimization significantly leads to maximization of the product yield. So, maintaining that particular temperature values inside that combustion chamber would particularly lead to the production of a good quality product. Then by controlling this temperature values, and if that temperature value matches or exceeds this AFT, so chemical processes can achieve higher conversion rates and selectivities. So these combustion processes would become highly selective, and in capacity of the same, the conversion rates would be faster. So industries such as petrochemicals, or you can say the pharma industries or manufacturing industry, they rely on AFTs, and thus this process optimization also. So this is one of the critical aspect of the application area. Then you have the third application area, which is the propulsion system. So the crucial area it is in designing and analysis of the propulsion systems, and those propulsion system areas may include the jet engines, or you can say the rockets or the gas turbines. So what is basically the idea behind this propulsion systems is by using or incorporating this particular aspect, we can optimize the design of that propulsion systems. You can see that the energy or that the engineers can optimize this combustion chamber designs or the fuel air ratio or the operating conditions, then thereby enhance the thrust and the fuel efficiency, right. And these AFT calculations basically they influence the propulsion systems performance in various the aerospace or transportation systems. So basically the crux of all these thing lies in one of the context that it is basically helpful in designing of the particular combustion chamber, be it the propulsion system or be it a combustion chamber or be it a combustion reaction. This particular AFT is applicable. Now we will be coming to the formula aspect of calculating this adiabatic flame temperatures. So this formula is basically related to the calculation of adiabatic flame temperatures, and that formula is negative of delta H over Cp plus the initial temperature. So this temperature, which is the adiabatic temperature, this is initial temperature plus a specific term, where this TAD represents this adiabatic flame temperature, delta H COMB represents the heat of combustion, and Cp prod represents the specific heat of the production mixture or the product mixture. That Cp value indicates the specific heat value, and initial temperature of the reactants is generally indicated with the help of T initial portion. So in the numerical problem you might have the value of initial temperature or the Cp value for a particular mix, and the energy or the heat which is produced in combustion, that can be provided. So from there you can easily judge what is the adiabatic flame temperature, and that particularly is applicable in designing of the combustion chambers as well. We stop here for a short break. After coming back from the break, we will learn the concept of adiabatic flame temperatures with the help of a numerical problem.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back to S. Chand Academy after the break, and we are learning the concept of adiabatic flame temperatures. Before going to the break, we have learnt the formula aspect of adiabatic flame temperatures. Now we will implement that concept in a numerical problem. So I am straight away coming to that numerical problem, and the numerical problem states that we would be considering a hypothetical combustion reaction wherein this methane, which is CH4, reacts with oxygen, and that forms carbon dioxide and water. This is a general basic combustion reaction in which a hydrocarbon reacts with oxygen to form carbon dioxide and water. And you are given with the heat of combustion, which is having this value minus 890 kilojoules per mole, and the initial temperature of the reactant is mentioned 25 degrees Celsius. So in general practice, we generally convert this degree Celsius temperature value into Kelvins. So I have converted it into Kelvin, and the specific heat capacity of the product mixture as assumed as follows, which is Cp for that carbon dioxide value is 37.1, and Cp for the water value is this given to us. So you know what is the formula, and we've discussed the formula before going to the break. Now putting in the context, I need to find out the adiabatic flame temperatures. So this is the formula presentation, which is adiabatic flame temperature is equal to initial temperature plus a term, and that term is delta H for the combustion process and Cp of the product mixture. So you are given with this initial temperature value. So you can see that the initial temperature value is mentioned to you as 298 Kelvin. So we have substituted this 298 Kelvin value in the expression. Now we are left with this delta H combustion. So delta H combustion value is given to us as minus 890. We have substituted this minus 890 term in this expression, and Cp for the product mix is to be determined. Herein we have this particular reaction, which is methane plus oxygen gives us carbon dioxide and water. This is an unbalanced reaction I am writing, but there are two products which have been formed, and the specific heat of the two products are given to us. So what I need to do, I need to check whether how many moles of the same is to be produced. So on balancing, you will come across that you will have 1 mole of carbon dioxide and 2 moles of water in the product side on balancing. So if you have 1 mole of this carbon dioxide, so you need to multiply the specific heat by 1, so into 1, and this 75.3 is 2 moles, so you need to multiply it with 2 moles, so that a complete Cp of the product mix can be calculated. So substituting all these values, you will get this adiabatic flame temperature as this value, which is 2353 kelvins. So this is the particular value, because this would be summed up with this particular part. Now we will be coming to the specific application areas in engineering related to the concept of adiabatic flame temperatures. So these are certain application areas in which this adiabatic flame temperature is applicable, in which number 1 is combustion engineering. Combustion engineering is one of the concept, one of the application area. Then you have the chemical engineering area, environmental engineering aspect, aerospace or propulsion systems. Then you have energy production sciences, and later material science and engineering also, and safety engineering also utilizes this adiabatic flame temperature concepts. So we will be discussing all of them one by one. So first thing is combustion engineering. So I have told you that adiabatic flame temperature is basically utilized in designing the combustion systems for power generation, heating and propulsions. So engineers basically rely on this adiabatic flame temperature calculations to optimize the combustion conditions. So for the foremost thing is to optimize those combustion conditions and getting the air fuel ratios optimum value and those operating temperatures so as to achieve this maximum efficiency and to minimize the emissions. This is one of the critical aspect. Then the another aspect is chemical engineering. So what this chemical engineers basically use this AFT part. So it serves as a critical parameter in designing and controlling an exothermic reaction. So if it is an reaction in which the heat is released from the particular system and you want to analyze that particular system for the optimum values, then this AFT serves as a critical parameter. And when you maintain this parameter or the temperature close to this adiabatic flame temperature, so chemical processes can achieve higher conversion rates and it may lead to increase in that product yields. And they are applicable to certain industries such as petrochemicals or pharmaceutical industries, or you can say some of the specialty chemicals. Then there is a categorization of environmental engineering in which it leads to pollution control. This AFT would lead to the pollution control. What aspect of the pollution control? By aiding the combustion system with the reduced emissions. So when the reductions are there in the emissions, so ultimately the environmental engineering aspect would come into existence, and these technologies are basically applicable to getting out the strategies of mitigating those pollutants such as NOx or that carbon monoxide emissions. Then you have aerospace and propulsion systems. This is another aspect in designing and optimizing the propulsion systems as discussed in that initial part, in which we generally use this AFT calculations to determine the maximum temperature reached in the combustion chamber for the particular rockets, or you can say the gas turbines or the jet engines. And this AFT information is practically helpful in selecting and optimizing the engine performances. So this is related to the propulsion systems. Then in case of material sciences, that many critical components of the different aspects are basically relying on this material selection aspect, such as the combustion chamber or the turbine blades, which are in close contact with those high temperature values. So we need to undertake, or we need to be very particular about those materials that can withstand temperatures which are reached during the combustion processes, and without hampering any structural imbalances in the particular material. So without any compromise of the structural integrity or the performances, we have to take care of that particular situation. And ultimately it leads to the case of safety engineering, or it is basically applicable to the safety engineering for assessing the risks which are associated with high temperature processes and designing appropriate safety measures, because AFT is basically that particular temperature which is related to safety, and that basically gives you an idea on which the temperature values which can be safer for the industrial practices. This basically predicts the worst scenarios during the accidental releases and the flammable materials, and as per the protocols which are particularly there. So with this we come to the end of the video, in which we learnt about the adiabatic flame temperature, its numerical aspect and the application areas of the same. Thank you.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, Please like, share and subscribe. And do not forget to press the bell icon.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.